do the recording. So let me do a brief introduction of Dr. Ken Wolgemuth. He founded Solid Rock Lectures to communicate the wonders of God's handiwork in geology. He has a PhD in geochemistry from Columbia University and 40 years career in petroleum industry. He was drawn into Christian worldview apologetic a decade ago, becoming a Colson Fellow in 2017. He has given numerous lectures about creation and co-authored a 2018 paper on radiocarbon dating, published in ASA's Perspectives on Science and Christian Faith. He is a contributing author to the groundbreaking book written expressly for the church, The Grand Canyon, Monument to an Ancient Earth. Can Noah's flood explain the Grand Canyon, which we're going to be hearing next week. So without further ado, take over, Dr. Wolgemuth.
Okay. Now I will make a comment that because you have heard me a couple of times before, you will see a few repeated slides, but not too much, okay? I'll be showing a few of my introductory slides that I just leave in there because this is prepared for audiences to take to Atlanta or wherever else it might happen. And then because plate tectonics is so important in maintaining suitable nutrients adequate for life and keep the nutrients circulating, I will be showing a few of the slides that reference plate tectonics, which we did have in one of the talks that I gave you 2 years ago. So there'll be some repetition, but not too much. Another comment I'll make is I don't mind questions asked during the talk, in that if there's something you want to, there will be a few times when I will stop, but if something comes to your mind, jot it down or just sort of jump in, that's okay with me. So let me go ahead and proceed with getting it running so that you should see the whole screen. And can I get that guy out of the way? Yeah, okay. So can you see my title slide, Expressing the Glory of God Through Geology?
Yes.
Is that okay? You got it? All right.
Yes.
And then I need this one. I'm getting something prepared here, so I have a marker up on the screen. Yeah, okay, there we go. I think of this, of my efforts like this as basically talking about creation story. So I have this slide of the Grand Canyon in here on a regular basis. So that's one that I like to have. And I want to just get my own slide up there in the corner. All right. I love this picture of a volcano because I can tie into Psalm 104. He touches the mountains and they smoke. It reminds me that God's involved with his creation and his sustaining power is part of that. And the whole theme here is we will see how God has his sustaining power continuously through looking at the earth. And then he invites us in Job also to look at the fish of the sea, look at things, and it will inform you. We can learn about God's creation by examining it. Speak to the earth and it will teach you, and let the fish sea inform you. Johannes Kepler is a well-known astronomer from centuries ago, and he was a Christian, and he made this quote that I love. The chief aim of all investigations of the external world should be to discover the rational order and the harmony that is imposed on it by God. So he is acknowledging God as the creator, which I do in all of this talk. Numbers of books have now been written about the way that the Earth is unique. In this case, the title is The Privileged Planet, written by Guillermo Gonzalez and Richard J. Richards. How our place in the cosmos is designed for discovery. They found, as they look at the universe in all kinds of parameters, that it is extremely fine-tuned for life and also for discovery, which we will see in a couple different examples. I was attending a meeting at my church where there were different ministries around. They're sharing their local ministry, and one of the folks there was an amateur astronomer. And I got talking about creation, and he says, you know what? He says, God has put us in a bedroom with a spectacular view of the universe. And I found that so catchy that I included here. The fact that we have a transparent atmosphere is just phenomenal. And that's the key feature that makes us be able to see the universe as well as we can. So there's astronomers' description of what our galaxy is like. And you'll notice that the Earth and the solar system are right there in an arm, or kind of between the arms of these collections of solar systems in our galaxy. So it's a space where at night, it's a location at night that we look out to the night sky and it's dark and we can see stars. Another book that's written on this topic is by Hugh Ross. His is called Improbable Planet: How Earth Became Humanity's Home. And I love the chapter titles that he put into this book. Things like the construction materials, the right neighborhood, the foundation, we have air conditioning, and it's ready for occupancy. So the construction materials, of course, the Earth, the right neighborhood, you'll see it's the right neighborhood in our solar system. And the foundation then is the fact that we are here on the Earth. Air conditioning is the control of temperature on the Earth by the processes that I will be describing. He emphasized in his Improbable Planet that it demonstrates God's divine nature. And one of the key things that I'm going to develop and explain is the Earth's magnetic field, which protects life from damaging radiation. And then plate tectonics, which I will develop in some of the slides, helps maintain suitable conditions of life because the nutrients get recycled back into the Earth's surface and in the locations where food is produced. Hugh Ross came out with another book on a similar topic, in which he called this one Designed to the Core. And this came out just a couple of years ago. And he has 12 chapters about astronomy. And he has about 5 chapters on the Earth and the Moon. So I'm going to make a choice to say a few things about astronomy, not too much, because I don't know much about it, but to sort of set the stage. And then I'll be digging into the things related to the Earth in particular. I'm going to show a couple of slides that come from what's called the John 1010 project. This is done by a videographer and a ministry that produces movies and produces movies for the Christian church to demonstrate the glory of God. They have lots of things about the biosphere in terms of the way birds migrate, and it's just exquisite photography. So if you want to see fabulous photography about the biosphere and God's creativity, look up the John 1010 project sometime. In this case, this is a description of a computer model of the universe that just shows the evidence that there's trillions of galaxies and galaxy clusters out there. And, our Milky Way galaxy is going to be somewhere in there. And in those first 10 chapters of the book, Hugh Ross develops all the details of the astronomy that's behind having the Milky Way galaxy here where it is. Now, there's an interesting thing about the production and the differences of what happened with all of the elements and where they came from. Of course, you recognize this as the periodic table of elements that has all 92 elements and the man-made elements there at the bottom. So this is what we know we actually have. The mass of the universe has to be very precise for us to, in fact, have all of these elements that make life possible. If the universe were not as massive as it is, no, if it were slightly more massive than it is right now, we wouldn't have hydrogen and helium and carbon and oxygen and nitrogen. We'd only have the elements from iron on up to uranium. Wow. I don't know how astronomers figured that out, but I leave that up to Hugh Ross and his brand of scientists. On the other extreme, if the universe was slightly less mass than it is right now, there would be no other elements except hydrogen and helium. Now, when I see this slide, I think, isn't that crazy? But again, and Hugh develops that in his book in terms of the design to the core, in that the mass of the universe has significance in terms of what elements are here. Now, where do all those other elements come from? Well, they come from the nuclear burning of hydrogen and gradually other elements in stars, and then in supernovae explosions. That is, the big one happened, of course, with Genesis 1:1, where God brought space, time, and energy and matter into existence. And of course, the public, or publicly, it's nicknamed the Big Bang. I use the word big flash here because a friend of mine here who is an engineer in Tulsa said, you know, it's not a bang in the sense of it's not chaotic, it's very precise. So he said, I call it the big flash. And I sort of like that because flash makes a little more sense in terms of how well ordered the whole event was. So in laboratories, nuclear physicists have produced all those heavy elements in particle accelerators that are in that periodic table. The mechanism of getting to everything else that is astronomical is that there's hydrogen burning in stars, there's helium burning in stars, there's carbon burning in stars. Each of those steps fusing protons and neutrons into larger nuclei, and then eventually explosive nucleosynthesis is the step in which the rest of the heavy elements are formed. So there's a picture of our sun. The sun is dominated, of course, by hydrogen. And so it is basically a small nuclear furnace of hydrogen being fused into helium. So that's the fusion process that occurs with the mass of our own star, the sun. Now, we are actually at a status where there have been about 3 or 4 generations of stars, because the new stars that were formed in the early part of the time of the universe 13.8 billion years ago just had the hydrogen and the helium, and they produced elements up to about carbon. After successive generations of stars, then gradually carbon and oxygen and nitrogen and magnesium and other elements were inside these red giant stars. So you can see that there are layers in this one. This massive star is near the end of its life, and it has sort of an onion-like structure in the interior that astronomers have figured out or understand or modeled. And you'll notice that there's iron and nickel in the core. So that is, this huge red giant star has layers of heavier density on the inside, as the Earth does also, and lighter material on the outside. So when the nuclear furnace gradually burns up and it's time for this one to basically die, it collapses in on itself. There's a nuclear burning explosion, and that explosive effort, or that explosive blast, ejects all that material into space, and it's in that supernova explosion that the pressures and temperatures get so high that then the elements from iron, nickel, and on up to uranium are produced. Incredible. So chapter 9 of Hugh's book has this in terms of the unique features of the sun. It appears to have no twin, and among the hundreds of billions of stars in our galaxy, none possess all the specific features required for advanced life to exist. Thanks to its mass, its age, its unique interior structure, its elemental composition, the sun maintains its luminosity, 5 times greater stability than any other known star. Currently, its flaring activity level and emission of dangerous radiation fall below that of any other known star like it. These optimal features, along with the sun's optimal orbital position about the center of the Milky Way galaxy, hold major significance for the possibility of life. So we are in what is nicknamed, and I'll show it in some slides, a Goldilocks zone of our galaxy, or of our galaxy. So God has designed the Earth and fine-tuned it for life. Now, what's some of the geological evidence is there that it is designed and being so completely unique? And I'm recognizing a gentleman that works at the Discovery Institute. He's trained as a geophysicist. His name is Casey Luskin, and he provided his version of this talk to me, which gave me a chance to improve and add my section here when I talk about the water in the atmosphere. That significantly came from Casey Luskin. Going to do 4 different themes: the Earth's magnetic field and its significance, plate tectonics and its significance, components related to water and why it is somewhat of a surprise that we have as much water as we did. Again, it's from God's design. And then finally, our very completely unique atmosphere that we have here. Okay, I showed the table of elements before, and now I'm going to highlight specific elements: hydrogen, helium. Those are the ones that burn heavily. There's iron and nickel that are critical inside our own Earth. And then there is uranium and thorium and potassium, all of which are radioactive atoms with long half-lives on the orders of 1 to 4 billion years. And they are very, very significant in terms of how much of those materials, how much of those radioactive atoms were in the stardust when our Earth was formed as part of the formation of our solar system. So, a bit about the interior structure of the Earth. In this case, there is a solid inner core that has temperatures up that you can see on the white in this, with temperatures up to 5,500 degrees Celsius. There's a liquid outer core in the yellow with temperatures 4,400 degrees Celsius. And then there's a mantle, which is plastic type material that's here in the red, that at the boundary with the core is about 4,400 degrees Celsius, and then obviously much less as we're up near the crust. And then the crust that's around the Earth is approximately up to a maximum about 25 miles, and in other segments and other areas of the Earth, it's about 5 to 10 miles, depending on the thickness, and we'll be looking at the plate tectonics in a little bit. So that's kind of the overall structure of the Earth. This gives a little bit more detail, and on the upper right of this slide, I again emphasize that the stardust that formed this solar system, including the Earth, had plenty of just the right amount of uranium-238, thorium-232, potassium-40, that as that was in the Earth, it is a significant factor to get the Earth's interior temperature high enough so that we have a liquid core. And this liquid core is composed significantly of iron and nickel. Okay, and I'm going to show some diagrams of the way the liquid core, the outer liquid core, moves around. The inner core is basically fairly solid in iron and probably some nickel also, nickel iron. And here are some temperatures that are shown also for emphasis. There's the mantle in red that's kind of plastic, and it has the silicon and the oxygen and the aluminum and the iron and magnesium and calcium and potassium and sodium and many of the others that make up the dominant amounts of rock that are in the mantle and then in the Earth's crust. So now we're just looking at the liquid portion of the Earth. So this would be inner portion of the core. So this would be the Earth's core. The mantle would be outside in the white in this diagram. This is what they consider it looked like, would be like 4 billion years ago in terms of the early development of what's called the dynamo that ends up causing us to have a magnetic field that's strong enough to achieve the safety of animals that live on the Earth's surface. Over a period of time then, and the way the Earth is today, it's the inner core that's solid, and then it's the outer core that's liquid, where the currents of the nickel iron are moving around in various ways that geophysicists just seek to their best they can to model these and get some understanding of how the magnetic field is generated. Here's another diagram that's kind of similar. The currents of the iron and the nickel from the outer core are convecting and also related to the Coriolis force. And the boy, I'm not pronouncing that right. Coriolis force, there I got it. Coriolis force is a factor that, because the Earth is spinning on its rotation, in terms of rotating it, one rotation in 24 hours, the movement of the water and air currents on the surface of the Earth tend to rotate in a clockwise way in the northern hemisphere and counterclockwise in the southern hemisphere. And these are because the Earth's ocean is on a curved surface that's rotating, and the Coriolis force is part of that process. This results then in moving electric currents that are happening because of the liquid and the Coriolis force with the Earth's rotation, which ultimately generate the magnetic field. Now, other folks have built other diagrams, so I'm just showing this as a different kind of diagram that other geophysicists have developed and show some of the lines of the magnetic field and that dynamo process that's on the interior, triggering the fact that we do have the magnetic field then. So the significance, there's the model of the Earth. You can see the lines of the magnetic field come out way outside the Earth. You can see the solid core, the liquid inner core, the mantle, the crust. This basically is critical because it deflects harmful solar radiation and galactic cosmic rays that damage DNA in anything that's living on the surface of the Earth. And it protects the atmosphere also from water vapor from being stripped off by the solar wind. So apparently water is of a weight that the wind from the sun that goes out toward all the planets, through all the planets, would strip water away if there were no magnetic field. And of course, without water, there's no life. Here's a diagram now of the solar wind coming from the left-hand side of the screen, the Earth, the magnetic field, and you can see how the lines of the solar wind get deflected around the Earth, giving it protection so it just doesn't come in and blast us. Some of this solar radiation and cosmic rays do tend to come down into the atmosphere above the north and the south poles, okay? Because the way the magnetic field is shaped, there's kind of a hole in it, if you will. So some of that gets down there, and that solar radiation, cosmic rays, are what causes the aurora borealis lights in the northern hemisphere and the similar in the southern hemisphere. Okay, well, our Earth is positioned such, or our Earth has a composition such that it is the only terrestrial planet that has this strong magnetic field to protect life. So Venus doesn't have it strong enough, Mars doesn't have it strong enough. And of course, the ones further away are gas giants, not suitable for life anyway. So, is the Earth's magnetic field unique? You bet. Any questions there at a bit of a pause?
Hey, Ken, can you explain what causes the changes in polarities if there's such thing as the North Pole becomes South Pole become North Pole?
Yeah.
Throughout a long time.
Yes. I won't jump out of the slide set now, but I will show some of those, say once we get finished and I come out of the PowerPoint. The Earth's magnetic field, that those magnetos, that the nature and behavior of the magnetic field has a couple of different factors that affect its stability. It's reasonably stable, but at the same time, it goes to stronger strength, and then it goes to weaker strength. So the strength goes up and down through geologic timescales, okay? When the strength gets fairly low, there are times when the field gets so low, and then when it begins to build up again, it goes in the reverse polarity. So during times of a magnetic reversal, if we had a magnet that was pointing toward the north now, it would point toward the south in a reverse polarity condition. And then I'll show you some diagrams of how frequently that has happened. As I was in school years ago, the most recent reversal was back at about 700,000 years. Currently, I think they have found some others that have had reversals in short time windows that didn't last very long. Overall, during the geologic timescale periods of the Mesozoic and Cenozoic, there have been something like 200 plus reversals in that area. And I will show that diagram then at some point. Okay. But thank you for asking that. Yeah, Ron, go ahead.
I suppose that we know that the Earth's magnetic field is unique because they've observed not as much aurora borealis and aurora australis on other planets, but is it just a matter of, do we have any idea why the Earth has all this iron and nickel at the core that create the magnetic field? And also, I thought that in the core, it was radioactive thorium that created the heat that heated up rock and created the tectonic plates. So where does the thorium?
Right. Yeah, you're exactly right about it. It's the thorium, radioactive. It's uranium-238 and 235, and it's also potassium. So you're right about the thorium, but thorium isn't the only one. It's basically three dominant radioactive atoms that are in the Earth that provide the heat. Now, your first part of the question was what again?
I suppose that they know that Earth has the best magnetic field by observing a lack of aurora borealis in nearby planets. Is there any theorizing about why Earth does have the amount of iron and nickel to create those fields?
Well, I was saying in the context of the design of the Earth.
Yeah.
That as God has guided the various stars and galaxies over timescales from the Big Bang 13.8 billion years ago, each successive stage of stars that are born and then die away have increasing amounts of heavy elements because it's the supernova explosions that produce the heavier elements from iron on up to uranium.
Mm-hmm.
So then the God, in my view, the God sustaining his creation arranged for the right amount of those radioactive elements to be in the stardust from which our solar system condensed with the sun and then the respective all the planets out from the sun.
Yeah.
And also, if I can jump in, I'm an astronomer, so I can say a bit
go ahead.
I can say a bit more about it because Venus and Mars, the composition isn't all that different. But to have a magnetic field, you need a rapidly rotating core. And Venus has an incredibly slow rotation. So its core simply is not rotating fast enough to generate a magnetic field.
Okay, thanks.
And Mars has a rotation similar to Earth, but Mars's core is completely frozen. It's completely solid. So you no longer get those currents you need to generate the magnetic field. So only in Earth do all of those requirements come together.
That's a good way to say it. Yep. Okay, any others there? Let's press on. Okay, there's the Pacific Ocean. And in the Pacific Ocean, you know about the Hawaiian Islands. And on beyond the Hawaiian Islands, there are emperor seamounts, which were formed in the same way, but the depth of the sea depth has taken those down below the sea surface. So they aren't islands on up there, on up to Alaska. The formation of these islands is understood to be a hot spot, which is in the mantle, which is now basically under the big island of Hawaii. And that lava on a regular basis is a plume of magma that comes up through the asthenosphere and through the lithosphere crust of the Pacific Ocean basin and spews out on the big island today and has spewed out, forming all the other islands gradually that are on to the north. So one of the examples that help us to understand the reliability of radiometric dating is that all the Hawaiian Islands and other islands on up to the Aleutians, the islands and the seamounts, we've on regular intervals up through there where we can get samples by a dredge down on the seamounts. We get igneous rocks up to the surface and take them into the laboratories. And we do a potassium argon radiometric dating step on those to understand how long ago that particular piece of rock was formed from a liquid to a solid. And the ages are shown then in terms of the Hawaiian Islands. The big island is about, ages from recent up to about 400,000 years. The island that has Honolulu is about 3 million years. And then the one that's to the northwest, that's part of the state of Hawaii, is about 5 million years. And then the others successively get older and older and older. And because we have a distance and we have an amount of time, we can recognize that on average, that movement of that Pacific Ocean plate is moving about 2.9 to 3.1 inches per year. So it's a tremendous example of how we can identify and have a level of confidence in radiometric dating because they fit together. If radiometric dating didn't work at all, those numbers wouldn't make sense. They'd be all over the place. I'm going to stand up just for a moment because my sunlight's going down and I left my windows with the screens open. So I'm just going to take 10 seconds and close them. I don't care to have the neighbors watching me in here sitting at my computer with a bright light on. Okay. On the lower right there, I have a beaker showing a Bunsen burner. So as the Bunsen burner heats the water in the middle of the beaker, the water rises. And because it's constrained in the beaker, the water that rises will gradually descend and sink around the outside edges. Well, in the case of the Earth's core, you remember a few minutes ago, we've been talking about that the outer core is liquid and their temperatures up here at the outer core mantle boundary, about 4,400 degrees Celsius. Well, that's hot enough to heat up the mantle, the lower mantle, at locations, and that mantle rock slowly rises. Remember, it's kind of plastic. It's not solid, rigid rock. It's somewhat plastic. So it rises up, and that process then causes these large convection cells of this plastic type liquidy rock to rotate like this and going around that side of the mantle and like this on the other side. And the movement of that mantle rock underneath the oceanic crust carries the continents apart from each other. And this is basically the way that one big supercontinent called Pangaea eventually broke apart, separating North America from Africa. I have a diagram that I'm going to show in an animation here in a moment, and I have this slide just to reference my appreciation for Professor Tanya Otwater at UCSB that prepared these and gave me permission to show them as much as I want, as long as I included a reference to her work there up there at UC Santa Barbara. Pangaea was together like this about 180 million years ago, which is middle Jurassic time. And now when I play the animation, you'll see the ages gradually, 140, 20, 100 million, etc. So that's a really good sort of view of the nature of what's happened over the last 180 million years to split up Pangaea into what we know today. This diagram shows the fact that the youngest rock here is at that mid-Atlantic ridge. It's red, that happens from that convection cell down in the mantle. The yellow is older, the green is older yet, and then the blue is the oldest of the Atlantic Ocean crust, oceanic crust, when North America and Africa first started separating about 180 million years ago. The average of that separation continues now at about 1 inch per year. So this separation is somewhat slower than is happening out in the Pacific Ocean basin, where the movement there is about 3 inches per year. Okay, so much of the life of life on the Earth is in the oceans, and in the oceans, all the corals that grow need calcium, carbon, sulfur, phosphorus, nitrogen to thrive. So all the plankton that are single-celled organisms and all the corals you can imagine that are on the Great Barrier Reef and in the Caribbean, these are constantly removing those critical elements to life, and they're locking them up in the sediments. So it gradually is a process where that life in the ocean depletes the ocean of these critical elements that make life possible. The overall cycle then, where those are being removed from the ocean basins gradually are carried by plate tectonics and are built into edges of the continents. So one example, for instance, is the Pacific. One of the Pacific plates is crashing into South America, and it has formed the mountains in South America, formed the Andes, and then the Andes are up at high elevation, so they undergo weathering, erosion. Those elements that were carried into the deep sea sediments gradually get recycled because of weathering processes and through volcanic rocks that come up because the volcanoes are at the edge of the continental masses in this plate tectonic process. Of course, rainwater is part of the process of the water cycle. And so there is output of evaporation safe into the sediments that take place as these elements are moved around. So here's the feature of plate tectonics keeps the nutrient cycle is the theme of this slide. Another example, and then a point of from a quotation. The tectonic recycling of the oceanic and continental crust holds the key, and it's balanced against the continental massive loss of minerals to the seabed. Tectonic recycling replenishes the oceans with continental runoff and by the reaction of water with upwelling magma at the mid-ocean ridges. Summarized there in a book written by Michael Denton, The Wonder of Water. So plate tectonics do what for us? It promotes the biological productivity. It helps to promote diversity in the sense that it's a hedge against mass extinction of a lot of species. And then it also has a factor in helping to maintain equitable temperatures that are necessary for animal life. We'll talk more about the temperature balance toward the end of the talk. In another book that was written about how rare the Earth is, it's with authors that use that word exactly, rare Earth, Brownlee and Ward, they said, it may be that plate tectonics is the central requirement for life on a planet, and that it is necessary for keeping the world supplied with water. And of course, you folks out in California, maybe you're tired of the heavy snows, but boy, it's going to provide water. So is the Earth unique? It sure is, because it is the only planet in our solar system that has plate tectonics. Any questions you might want to ask there? Ron?
How does the plate tectonics provide water? Wouldn't water evaporate anyway if there were
Oh,
water?
yeah, okay. The water cycle, yeah, you're right. The water cycle itself is not automatically tied to, but some of it is water related in that when ocean sediments get carried down into the upper mantle, they would have some excess water just because of the water stuck with the sediments. But no, the dominant water cycle does not depend directly on plate tectonics. I agree with you. Good point. I may have maybe I didn't word that quite correctly in that.
Yeah.
Another one?
So in other words, to explain about plate tectonic, isn't it like not a vacuum, but how do you so recycling all the dirt, all the debris, all the excess at the ocean bed where the mantle go under where all these debris settlements sitting down the bottom and then went under the mantle and get recycled again. Basically, it's a washing machine, basically.
Yeah, it's somewhat that. Yeah.
Okay.
It's getting the important elements of life recycled back up to continental crust for weathering and erosion. Okay, let's look at water. 4 requirements for the planet to have liquid water and sustain life. The planet has captured enough that we have a large ocean, of course. Water has migrated from the interior up to the surface gradually over geologic timescales. Water is not lost to space excessively. And of course, it exists here in a temperature range that exists as a liquid. Now, these 4 things actually come from the individual whom the Lord guided to be my thesis advisor. His name is Wallace Broker, and he was always known as Wally. He was that kind of style of person. And he wrote a little booklet, a book called How to Build a Habitable Planet. And there is no liquid other than here, but possibly Mars had some at one point, but it's not on the surface right now. So
Just had to say, I used that book as a textbook in one of my classes in undergrad.
oh, did you?
Yeah, I had a class called, I went to Georgia Tech. I had a class called How to Build and Maintain a Habitable Planet. And that was our textbook.
That was the textbook.
Yeah.
I just decided that, well, he wrote this in 1998 and I was strictly in the oil industry at that point. So I didn't end up buying it, but I realized I should, because I've read so many of his endless papers. So I had this content material when I was there in graduate school. And I just realized, I think I should get a copy myself to have a reference to it. And then I could get some other quotes into it. But the Lord really blessed me to be able to do my thesis under such a brilliant man who God just gave him intellectual gifts beyond imagination. Here's the way he puts it. The Earth is about 1/2 of 1% by weight of water, and the factors that lead to this particular capture efficiently are not understood. Based on observation that the Earth is depleted in potassium and other moderately volatile elements, our planet would not be expected to have any water, but somehow Earth just got about the ideal amount to support life. So there's a riddle that isn't well known or wasn't well known back in the 1990s, whether he he died about 5-6 years ago. I don't know how he would write it if he were writing it, how much more they learned about the source of water, but that was the situation there just before the turn of the century. One of the factors in the solar system is there's what's considered a frost line, which is an important concept as a frost line beyond which volatile elements as water, or volatiles such as water, condensed and remain in a solid state as ice. In the early solar system, the snow line was between the orbits of Mars and Jupiter. That means it was somewhat further out at some point. So part of the riddle of understanding the nature of our Earth having water. Here's one person that describes a solution maybe to the mystery. The origin of the Earth's water is debated. The inner solar system was too warm to have retained water ice, so terrestrial water is thought to have been supplied by hydrated minerals that originally formed in the outer solar system and then migrated inward. Now, don't ask me how that could be, that migration. That when I read this, I thought, man, what's happening there? And I don't have an answer to that. I am aware that there, even deep in the mantle, there are certain minerals that do have some trapped H2O, okay? In some ways with their crystal lattice. Again, it's not a subject that I've dug too much into, could do some more research into that. But it is baffling that we have the amount of water we have. Well, it's unique that it has not lost its water over time. Unlike Mars and Venus, our water's been maintained. Venus's water is lost, and Mars and the water from Mars has been lost. So that delicate balance, again, it's designed and fine-tuned for life. It's possible that there's no other Earth like this anywhere in the universe, but we won't know. Any questions about water? One of the baffles where I'm sure a lot of research still done. Okay, let's look at the Earth's atmosphere. We are in what's nicknamed a Goldilocks zone. Air pressure must to be light enough to allow evaporation of water from the oceans. But the atmosphere also has to be heavy enough so that it destroys the asteroids that come bombarding into our Earth. You've heard stories about an asteroid coming in, one in 1906, I believe, that came blasting into Russia over Siberia and destroyed enormous amounts of land. So evaporation, of course, drives the water cycle on the surface of the Earth. So a thick atmosphere destroys the asteroids that explode in the atmosphere. And within the last year, I've learned that there's a hypothesis that the Sodom and Gomorrah story of being destroyed in the days of Abraham and Lot might have been an airburst from a small asteroid that came in at a low angle right there at the north edge of the Dead Sea. The Dead Sea in Israel. So it's fascinating to think that maybe God used something along that line. In fact, I found a passage in Psalms, or in, Isaiah. Let's see. No, Lamentations. I saw a reference in Lamentations that Sodom was destroyed instantaneously. It was kind of striking to find that when I learned about this not too long ago. Well, we have a Goldilocks zone of gravity. That is, the Earth's gravity has to be strong enough so that we don't lose oxygen and nitrogen, but it has to be weak enough so that hydrogen can escape from the atmosphere. So the size of the Earth is even critical. Earth and Venus are massive enough to hold all but the lightest gases. And of course, the Moon and Mercury don't have enough gravity to hold any gas. And again, this comes from the book that you had used in that class from Wally Broker, How to Build a Habitable Planet. The early atmosphere that we did have on the Earth was my little boundary is over top of the front. I knew there was another one in there. Yeah. Nitrogen, carbon dioxide, water, carbon monoxide, methane, ammonia, but there was no free oxygen. Okay. So we didn't even have oxygen for life in the early time of the Earth. The early atmosphere was very dark. We get that in Genesis 1:2. And darkness was over the face of the deep. Darkness was at the top because there was just so much carbon dioxide and so much methane in the atmosphere that it was dark at that time. And then gradually, because of the water, carbon dioxide get absorbed into the water, and gradually that carbon ended up in limestone rocks. So there was enormous amount of carbon dioxide that ends up with the rocks and the limestones that we have that are part of our continental crust. Plate tectonics got going about 2.5 billion years ago. Let me get this again, plate tectonics going there. I have a yellow line over here on the right that I've just put up there. And this is about the beginning of the Paleozoic, which is about the time window of the Cambrian geologic period. So prior to that, oxygen level was very low. And then shortly before the Cambrian, processes of photosynthesis that were happening built the oxygen level up into the atmosphere, up toward where it is today. So composition of the atmosphere, oxygen is high enough to sustain biological respiration that we have. So one of the things that I give thanks to, and when I'm having my prayer times, is I'm thankful for oxygen, because if we didn't have oxygen, we wouldn't be here. But also it's low enough, it's less than 25%, to prevent explosivity or toxicity to life. I guess if we have too much, we couldn't live either. Here's one reference that really surprises me, but it's stated. I haven't dug into this too much, but wet organic matter will burn in the air if the oxygen is over 25%. So it's got to have that balance. And here at 21%, it's right in a sweet spot of its for us. Nitrogen is 78% of the composition of the atmosphere, a little bit of argon, and all the others smaller amounts. Nitrogen really has unique properties that did not hit me until I got some of this material from a professor at Andrews University by the name of Ryan Hayes. And so I recognize and thank him for sharing his information with me. Nitrogen has the proper density. It's just about close to the same as oxygen. It's not a greenhouse gas. It can absorb ultra low UV radiation. It's not toxic to life. It's not flammable. It's hard to liquefy. It is transparent to UV, visible, and infrared radiation. It's not reactive. It's not acidifying the oceans. It has a low solubility in water, and it's usable by living organisms in the sense we do need some oxygen for life to exist. So it is an incredibly unique gas that has all these properties intermixed with the oxygen. So God just designed this so precisely. I just marvel at it. Here's the global thermostat. That's a combination of the plate tectonics, the water in the atmosphere, the right atmospheric cycle. If it gets too hot, there's more rain and there's more weathering, which removes carbon dioxide from the atmosphere and the earth cools. On the other extreme, if it gets too cool, there's less rain, and weathering. Carbon dioxide builds up in the atmosphere and the earth warms up because it is a greenhouse gas. So to combine these things together, there's a fabulous convergence among plate tectonics for carbon cycling, liquid water in large amounts, an atmosphere with carbon dioxide greenhouse gas, that we basically have a global thermostat that keeps a balance. So is the Earth unique? Sure is. We've got this strong magnetic field. We've got the plate tectonics. We have large amounts of water. We have this unique nitrogen, oxygen atmosphere to support life. And we've got this global thermostat that's really hard to imagine anywhere else. So is the Earth's atmosphere unique for life? You bet. Few summary comments then. The Earth is blessed with incredible good fortune, giving it all the right properties to stay in a complex and beautiful biosphere. Earth is a very strange place, perhaps the luckiest planet in the visible universe. Well, of course, I don't treat it, or we don't treat it as a lucky planet. We see God's hand in it as He created it for us. So what geological evidence is there that the Earth is designed and unique? Well, we're really going through it. God has really designed it uniquely. And again, I reference my thanks to Casey Luskin for sharing his talk that he's been giving for Discovery Institute. It's an individual that Dr. John Milam that's put together a whole list of important things that make the Earth unique. Fine-tuning of the Earth and all the probability. He's gotten something like 77 characteristics that are required for life, and I've just touched about 4 or 5 of those, 5 or 6 of those. He has 3.5 pages of parameters like this, of which working on probability has a feature to fall into some precise range for physical life. And he concludes there's less than 1 chance in 10 to the 172nd power that even one such planet could occur anywhere in the universe. So there's an example of the big, long list. So our heavenly body design here, it's a just right universe, the right super galaxy cluster, a right clustering group, a right galaxy, a right star, a right Jupiter, Saturn, Venus, etc., just a right Earth and just a right moon. Here again, coming from the John 10:10 project in one of their videos that I watched. Here on the left is a list of about 10 things, and on the right side, so overall he has here about 15 to 20. Correct type of home star, right distance from the sun, right rotation rate, optimum position in the galaxy, temperate climate, terrestrial composition, dynamic geology, a large moon, ozone, tidal movements, good axial tilt for temperature control, oxygen-rich atmosphere, chemical nutrients, protection from meteors and meteorites, mineral resources, and moving clouds. I love that whole big collection right there. Time to stop. I'll turn it now to Q&A. Thank you very much for listening.
Thank you so much, Dr. Wolgemuth. Earlier at the beginning, you have talked about right after Big Bang, the Earth, if the universe is a little heavy, then we will only have the heavy element in the periodic table. If the universe is light, a little bit lighter, then we only have hydrogen in the periodic table. We have in our presence Chuck Horse, who he's a professor of astronomy at UCSD.
Yeah.
UC San Diego. I think he is going to explain to us how does that happen. Hey, Chuck,
Okay.
go ahead.
All right, well, I'll just give a little bit of a oversight, not really in detail, but the mass of the initial universe affects the expansion rate of the universe. So
Oh, okay.
if there's a little too much mass, then the universe, it's going to be a closed universe, and that it's going to begin to expand, and then it's well, let me start with a light universe first. So if the universe is a little bit light, it's going to expand rapidly, and it's going to expand too fast, such that stars and galaxies won't combine, won't form. And if you don't have stars, then you're not going to have the heavy elements. So your one chart there showed that if it was a light, if the universe didn't have as much mass, it would only have the lighter elements. And that's because stars won't form if the mass is too light.
Yeah.
And if it is too heavy, then it's going to begin to expand, and you're going to have lots of stars in the very early universe. They're going to be very heavy, and they're going to evolve very quickly. And so you're not going to have the light elements, because at 14.5 billion years, or 13.8 billion years after the Big Bang, because the universe would have evolved quickly, and all those lighter elements would have already gone through fusion reactions and turned into the heavier elements. So your sample there is a little bit misleading. It's not that there's not going to be light elements on the one side and not heavy elements on the other side. It's just going to be a much more propensity, and there will be few light elements if the universe is heavier than it is now.
Okay.
And the amazing factor is the balancing point is so minuscule between a light universe and a heavy universe. That's where we get into the fine-tuning concept, and it's an astronomical precision
Yeah.
that allows it to continue to have expanded to 13.8 billion years, but not to have expanded too quickly. So
Okay. Could you send me an email? Has somebody calculated sort of the magnitude of that precision?
yes, it's like 10 to the 90th. Or
Okay.
no, it's 10 to the 120th. It's in Hugh's book. It's, and that's it's in Hugh's books. It's about 10 to the 100.
Okay, which one? Is it probably even in this recent one also, in Design to the Core, or maybe an earlier one?
Well, I had seen it in his earlier ones. I forget the name of it. I read it a long time ago.
Yeah.
But
Yeah.
yeah,
I
put it in
probably can
several.
find.
Hugh generally quotes 10 to the 120th.
Oh, okay.
Yeah,
Yeah.
he's put it in several because it's basically the fine tuning of dark energy.
Yeah.
Because
Okay.
ultimately it's dark energy that drives the expansion rate. And so you need, or it's a fine tuning, I think, it might also be of entropy, but you need to have dark energy fine tuned to that exact amount to get a universe that neither expands incredibly rapidly or collapses back in on itself.
Okay. Chuck, I wouldn't mind if you'd send me an email sort of highlighting that and maybe how I might adjust those slides that would be suitable. I'd be glad to do that. So, and John,
Let me send you my email.
You'll see my
and then we
email
can-
in the announcement. Okay, you remember somebody asked about magnetic field, okay? I'm going to show a couple slides here. That was not the right one to go. There we go. Okay. Can you see that slide? Reversals.
Yes.
Okay. Let's see here. Dark is polarity today, and the white is reversed. So there you can see it is not regular in terms of timing, okay? You know, there's no half-life to it. There's no every X number of years it happens. You can see that it's random. And in this case, there was what, about 1, 2, 3, 4, 5, about 10 different patches there of black. So each division is a reversal. So something like 15 reversals over the last 5 million years. And then I have one more.
And I would assume during that reversal, the protection will greatly degrade. And you know,
Probably so.
I don't know how long the reversal takes for the magnetic fields to build back up again.
Yes, and the other factor is, if it were really long, and in fact, we don't see evidence that the reversals of the magnetic field have damaged the fossil record. Okay? So from what I know, this seems independent of does not have an effect on the fossil record of the animals that lived. So I guess that means they must be very short, possibly very short. Another example. In the ocean basin, I showed the example you remember of the mid-ocean ridge. So in this case, the red, say, is normal polarity, and the white is reverse polarity. So this would be the most recent one that showed up on the black in that previous slide. This is a reversal to reverse polarity, and this was a previous normal polarity from before. So what's happened here, and now I'll go to this next slide. This is later, more time has passed. So here is, let's see, the white he's using is, the white is normal polarity and red is reverse polarity. So this is what's happened at the Mid-Atlantic Ridge. Well, this was the data that convinced the geoscience community that yes, plate tectonics moved. So this is the nature of the reversals from the Mid-Atlantic Ridge going eastward toward Africa and west toward North America. And you'll notice that the one side is a mirror image of the other side. And the magnetic data, when it was realized that that's a mirror image, they realized that yes, indeed, new oceanic crust was being formed at the Mid-Atlantic Ridge as the continents separated. And this happened, that recognition was in about 1967, which was basically 67 was the pinnacle year of the American Geophysical Annual Meeting, when this kind of data was shown, and the people that have been wrestling with all this data finally said, you know, those continents are moving and new oceanic crust is being formed. And that was sort of the pinnacle of the paradigm shift to plate tectonics. And I was at that meeting in 1967 in Washington, D.C. as a brand new graduate student at Columbia University. And of course, I was clueless. And I lived to be 50 years past that. And in 2017, my wife and I were able to go to the American Geophysical Union annual meeting in New Orleans, and they had a session on the 50th anniversary of that. And some of the old folks were there that I knew from Columbia University, and they were asked in the audience, how long did it take for you to put all this together once it fell in place? And they said, well, once they realized the nature of all this data, that it kind of was a bright light came on like, gee whiz, this really works. And plate tectonics took the day, and that was a 50-year anniversary celebration. Okay, I want to come out. And one other thing I want to show now, if I can get that sucker up. Oh, no, not there. There it is. Now, can you see that table that's called geologic timescale?
No.
No, not yet.
Okay, it's on my screen, but you can't see it. Is that right?
Correct.
All right, then I can't show you. Okay. What I'll do is I'll send this one geologic timescale to David, and he can send it to you by email. And what it is the Paleozoic, Mesozoic, and Cenozoic, and there's a column in there. I'll do a little word description that'll go along with it, and you'll see how many reversals have happened in the Mesozoic and Cenozoic. It's a couple hundred. Any other questions?
Yeah, I'm wondering, you said that carbon dioxide reduces when it's hot and then it is released when it's cold. What is the mechanism for that? And the other question is, you talked about the composition of the early atmosphere.
Yeah.
We know that now that the Miller-Urey experiment was conducted in something different from the early atmosphere, but how do we know what the early atmosphere was? Is it in fossils or something?
Part of it is going to be related to the sediments that are formed. There were lots of there was a lot of what are called banded iron formations that only started after a couple of billion years. Okay. And then much of the oxygen, the early oxygen that was formed by photosynthesis of basically single-celled organisms in the oceans, gradually when oxygen began to be formed, most of that oxygen was taken up because there was so much iron in the sedimentary, there was iron in the ocean, and so these banded iron formations became the sediments that were formed. And then the composition, the nitrogen's been there all along. We do see the evidence of when limestones were formed in the geologic record also, which is a manner of taking carbon dioxide out of the atmosphere. So the timing of different sediments being formed that we find on the continents is a big factor of understanding something about the composition.
Oh, yeah. Now, is that how carbon is taken out of the atmosphere when it gets warm with limestone? There was a slide you had where you said that when it's cold, carbon dioxide is released or something, or is that just meaning that on a planet that has a lot of carbon dioxide, it's hot if the planet doesn't have much carbon dioxide? It's cold.
When there's a lot of carbon dioxide in the atmosphere, the temperature is higher. Yeah,
Ah, yes.
because of its greenhouse effect.
Right. Hmm.
So there's clearly a very delicate balance.
Yes.
In fact, Wally Broker, my advisor, was noted for having a mind that he could put lots of stuff together from different disciplines across the geosciences. And one of his cartoon diagrams, as the science community has wrestled with global climate change, is that he had a big dinosaur diagram or a dragon diagram that he put in one of his papers. And then he had mankind represented by a man who was behind the dinosaur, behind the dragon, and he's poking his finger into the dragon's rear end. It's sort of like saying, well, we're poking our finger in, but we don't know how the dragon's going to react. That is, it is incredibly difficult to put the puzzle together of climate change. That was the point he was making. It's really hard to tell where the triggers are, and because the system is so complex. So it's
We don't know where the tipping points are, for one thing.
It's hard. Yeah, it's hard to know where the tip. Exactly. That's a perfect word. It's hard to know where the tipping points are for different cycles.
Mm. Mm.
Any others?
Well, Kevin Birthwell, our climate scientist, has several talk about that. I'm sure it's a complex issue. So for those who know, and the media and politicians who say that's a settled science, that's a total lie.
And Kevin, I remember I was able to listen to one of his, and of course he's a different person and he works in different things. So he had different kinds of detail in it than the way I presented it. So don't resist, if you can listen to his also, get his perspective and improve your knowledge and awareness that way.
Thank you so much. Do we have any other questions?
Well, you said that when the Earth has the only planet with a lot of water, now is that being protected from the solar wind by our magnetic field, probably? Or is it just somehow that it just got God created it with a lot of water originally?
From what I'm hearing, I wasn't keenly aware that there was that magnitude of a water problem, just because I haven't been following that research over the last 3 or 4 decades. I was in the oil industry. And it sounds as though it's just scientifically, it's a surprise that we have this much water. And it's likely a problem that research is still going on. Like, why do we have as much water as we do?
It isn't that we have a lot of water. It's that, that we have found planets that are almost entirely water-based.
Okay.
It's that we have a small amount of water, but it's stable and we've kept it. That's been the key. Typically, they think just like the climate change, once you reach that tipping point, they would anticipate that most of the water would leave quickly. So it's surprising that we have what we need to keep the water. But like I said, there are exoplanets that they think the entire surface is completely covered by water,
Okay.
and they think they've found some planets that are almost entirely water-based. So you don't want too much water because then there's no continents.
Yeah.
And if you also don't want so much water that there's no really core and protection by the magnetic field. So that's the thing is, you know, they thought Venus had water before as well, but once it reached that point and got warm enough, it just all went away. So it's not too hard to get rid of water. So it's very amazing that we have the protection to be able to keep, you know, just the right amount of water that enables us to have the planet that we have.
Thank you very much.
Mhm.